Hello everyone, welcome back to the course Design of Power Electronic Converter. In today's lecture, we are going to study one of the most important topics in the converter design, how to choose the inductor and capacitor values of buck converter. In previous lecture, we understood the operation of a buck converter and analyzed the waveform of the buck converter. Today we will understand why these passive components are important and how they influence the performance of a converter. By the end of this lecture, you will be able to understand the design procedures that is commonly followed for industries while developing a DC to DC converter. So before starting the mathematical derivation, let's understand the practical importance of inductors and capacitors. Buck converter is not simply made of switch and a diode. See, when we have learned our power electronics, we have studied the circuit diagram with only the switch and diode. But it is not actually simply a switch and a diode. Inductor and capacitor are responsible for making the converter particularly useful. The inductor stores energy whenever the switch is on and releases the stored energy during the turn off interval. I will tell you one more time. Inductor stores energy whenever the switch is in on condition. So just imagine a battery. So it will act like a battery. It will get charged and it releases the stored energy during the turn off interval. This continuous exchange of energy makes the load current smooth. Without an inductor, the current would become highly pulsating. Similarly, capacitor stores electrical charge. So what is the function of a capacitor? It stores the electrical charge. So its primary function is to maintain a nearly constant output current. So inductor maintains a current which is less pulsating and capacitor maintains output voltage nearly constant. Whenever the load current suddenly increases or decreases, the capacitor immediately absorbs or supplies current, therefore reducing the voltage ripple. So the inductor controls the current ripple and the capacitor controls the voltage ripple. So if these components are not selected properly, inductor and capacitor is not selected properly, the converter may experience excessive ripple, poor efficiency, it may cause overheating, unstable output voltage, increased electromagnetic interference. Therefore, selecting a suitable inductor and capacitor is one of the most critical stage in the converter design. So in this lecture, we will achieve the following learning outcomes. First, we will understand the role of inductor and capacitor in the buck converter. Second, we can derive the design equation used for calculating these values. Thirdly, we can derive the design or we can calculate the suitable values for these components, inductor and capacitor, with the proper specification. Then we will analyze how different values of inductance and capacitance affect the ripple current and ripple voltage. And finally, we will understand how engineers select the practical components of converter design. And we will do the design of buck converter based on this design. Now let's understand the energy transfer process. So this we have already discussed or explained in the previous lecture series. So whenever the switch is in on condition, see, we have two conditions. One is the switch is in the on condition and second one is the switch is in the off condition. So these are the two conditions. So here this circuit diagram, the first circuit diagram is like when the switch is in the on condition. So when the switch is in the on condition means the switch will be closed. So it acts as a closed circuit. Now, so when this is a closed circuit, this diode will be stagnant, or it is not having any action on the circuit. Your supply, your inductor, then your load. So this is our circuit which is active at that time. So this we have already discussed. So this is the circuit which is active during the turn on interval. So now we will understand the equations. So this we have already derived VL. VL is the voltage across this inductor. So voltage across the inductor, which can be written as L DIL by dt. This is the voltage across inductor. So it can be written as L into DIL by dt, which is equal to. So in this circuit, there is only supply voltage and voltage drop across the load. So VL can be written as V in minus V naught. And IC is the current flowing through the capacitor. IC is equal to C dVc by dt. Vc is the voltage across this capacitor. So IC is equal to C dVc by dt. So IC is the current flowing through the capacitor. So here this is a junction. So we can write IC is equal to IL, inductor current, minus I out, or load current, output current. So this is our junction. IC is equal Kirchhoff's current rule. So IC is equal to IL minus I naught. Now voltage across the switch. During the turn on condition, the switch acts as a short circuit. So voltage across the switch is 0. Then VD is the voltage across the diode. This diode is in reverse biased condition. So this diode will act as an open circuit. So voltage across this is equal to the supply voltage, because the diode is directly connected across the supply. So VD is equal to V in. ISW is the current flowing through the switch. Current flowing through the switch is equal to the supply current, input current, which is again equal to the current through the inductor. Current flowing through the switch is equal to the current flowing through the inductor. So it is written ISW is equal to IL, and ID is the current flowing through the diode. ID is equal to 0. So during the T on interval, these are the voltages and currents of various devices in this buck converter. Now the VL is the voltage across the inductor. So if we integrate the voltage from 0 to Ts for the entire cycle, the inductor voltage is 0, because it is discharging in the positive direction and discharging in the negative direction. So the average value or total value will be 0. So integral Ts to VL dt is equal to 0. So V out is equal to D into V in. So we can write this as V out is equal to D into V in, or D is equal to V out upon V in. So this is the equation of output voltage for a buck converter. Now IC is the capacitor current. So if we integrate for one cycle, again IC is also increasing and decreasing. Capacitor current is also increasing and decreasing. So the average value can be written as 0. Then IL is the inductor current is equal to the output current. So output is a resistive load. So because the I out is a resistive load, we can write as I out is equal to V output. This I out is equal to V out upon R. This is the Ohm's law, just applying Ohm's law. Now we will see the turn off interval, during the turn off interval. So when the switch is in off condition, so here when the switch is in on condition. So this is the switching. So when this is the switching pulse that we are giving to the MOSFET or IGBT, whatever it is. So this is switches in the on condition. We are giving a positive gate pulse, and off condition means we are not giving any gate pulse. Okay, so during the on condition, during the turn on interval, I have already told you, inductor will act as a battery, charging battery, or inductor will store the current. So it will get charged. So current will increase from the minimum value to a maximum value. Okay, and during the turn off interval, inductor release energy through this circuit. Inductor release energy during the turn off interval. So the path will be, so this is the path. The inductor release energy, so the current will be discharging. Okay, now we will see the output voltage. So this is the positive half cycle. Actually, there is a mistake in this drawing. So output voltage is positive during the turn on interval, and the output voltage is 0 in the turn off interval. So this is positive and this will be 0 in the and the switch is in the off condition. Now input voltage also. The input voltage V in is a constant value throughout. Input voltage is a constant value throughout, and VD, the voltage across the diode, is like during the turn on interval, there is a voltage across the diode, and during the turn off interval, your diode acts as a short circuit and the voltage across the diode will be 0. Now across the switch is short circuited during the turn on condition, so the voltage is 0, and it is open circuited when the switch is in off condition, so there is a voltage which is equal to V in is appearing across the switch. So switch current will be equal to the inductor current in the, we know that the current ISW is equal to IL, which is the current flowing through the inductor. So because they are equal, this same current IL will flow through the switch during the on condition, and when the switch is in off condition, there is 0 current flow through it. And diode is open circuited in the turn on interval, so it is 0, and diode is a forward biased condition. Diode will be forward biased condition in the turn off interval, so the current will be, there is a current flowing through the diode. Okay, this is also equal to, it is also similar to the inductor current, or inductor starts releasing through the diode. Actually current direction is this. This is the current direction. Okay, now we will analyze the circuit in the turn off interval. So during the turn off interval, or we can write this as 1 minus d into ts. So this is your turn on interval. This can be represented dts, and this is the turn off interval. This is represented by 1 minus dts. So in this interval, VL is equal to again L di by dt, but this entire portion is detached from the circuit. So we need not consider the source current, source voltage or supply voltage. So your voltage across the inductor is directly shorted with the load voltage. So VL is equal to L di by dt is equal to minus V naught. Minus V naught. You see the polarity. So it will be minus V naught. IC is equal to C dVc by dt, and this current is, IC is the difference in current. When we are taking this as a junction, Kirchhoff's current law, IC is equal to IL minus I out. Now VSW, voltage across the switch. So here voltage across the switch is V in. Voltage across the switch is equal to V in during the turn on condition. VD is the voltage across the diode. Diode is in forward biased condition. So voltage across the diode will be 0. Current flowing through the diode will be 0 and ID is equal to IL. ID is the current flowing through the diode. This is equal to the IL current. So these are the terms when we are considering the analyzing the buck converter. Okay, so here I have written a term CCM. CCM is nothing but continuous conduction mode. CCM is continuous conduction mode. I will explain you what is a continuous conduction mode. So here in this slide we have analyzed the circuit. This we have already discussed in previous lecture. So here you have to remember few things. Output voltage for a buck converter, output voltage V out is equal to D into V in, where D is the duty ratio. IL is equal to current IL, inductor current IL is equal to I out. That is the output current, which is equal to V out upon R. Okay, so this is the equations. Now we will derive for the inductor value. Okay, so here when we are designing this, we are considering the current is in continuous conduction mode. So here you can see the current waveform. This is the inductor current waveform. Okay, the inductor current is in continuous mode, means there is a current flowing through the inductor always, because your current is not touching to zero. So that means there is a current flow through the inductor throughout the circuit. Means whether it is turn on time or a turn off time, current is flowing through the inductor. So because that current is flowing through the inductor, so you see the waveform. So current is never touching this zero reference line. So this is considered as continuous conduction mode. So here, this is our circuit diagram of buck converter. This is the waveform of the buck converter. Delta IL. Delta IL is the peak to peak value. Delta IL is from here to here. This much is delta IL, and this is the average value of the inductor current. Okay, so average value is inductor current is IL. So this point, this total height is delta IL. So this peak point is IL plus delta IL by 2, and this lowest point of this inductor current is IL minus delta IL by 2. Keep this in your mind. Now we will see the inductor voltage during the on interval. So this we have obtained in the previous slide. VL, voltage across the inductor, is Vs, or V in minus V naught. Okay. Now this can be written as L into DIL by dt. So when you rewrite this equation, when you take this L to the other side, we can write DIL by dt, DIL by dt. So here DIL by dt is equal to Vs minus V out upon L. So this is the condition when switch is in the on condition. Now this DIL by dt can be written as delta IL. This can be written as delta IL during on condition. Okay, this is in the on condition. So here in on condition DTS. So on condition means on interval is nothing but DTS is equal to Vs minus V naught upon L, Vs minus V naught upon L into DTS. Now we will see the off interval. So during the turn off interval, VL is equal to minus V naught. So L, which can be written as LdIL by dt. So again rearranging this equation, we will get DIL by dt is equal to minus V naught upon EL. So here you can write this delta IL. Delta IL, DIL by dt can be written as delta IL of. So this can be written, this time period is 1 minus dTs, which is equal to minus V naught upon L into 1 minus dTs. Okay. Now, during the steady state condition, normal operating condition for an ideal buck converter, output voltage is equal to duty ratio into input voltage. Now, for the case of inductance, for finding the value of inductance, this delta IL is equal to delta IL in the on condition. This delta IL in the on condition, that is Vs minus V naught by L into dTs. Okay, so delta IL in the on condition, that is the inductor current. This is Vs minus V naught by L into dTs. This is the equation. So here for Ts, we can write the time period as 1 by Fs. So this is like just we have written Ts time period is equal to 1 by frequency. Time is equal to 1 upon frequency. So if you rearrange this equation, we will get L is equal to inductance value L is equal to Vs minus V naught into D divided by Fs into delta IL. This is one equation, first equation. Now here for ideal buck converter, D is equal to V naught upon Vs. So Vs minus V naught. Vs minus V naught can be written as Vs into 1 minus D. You just substitute this value here. So you will get Vs is Vs minus V naught can be written as Vs into 1 minus D. So when you rearrange this, we will get V naught upon D into 1 minus D. So now when you rearrange this, we can get L is equal to V naught into 1 minus D divided by Fs into delta. So these both equation, this is one equation, this is second equation. So in the another form, just rearrange it. So either you can use this formula for finding the inductance, or you can use this formula for finding the inductance value. So with this formula, we are able to find the value of inductance for this buck converter. Okay, now I have told you about CCM, continuous conduction mode. What is continuous conduction mode? You can see the current is always a positive value. Current never touches zero. The inductor current never, you can read this, inductor current never touches zero. It is always positive. So this is called a continuous conduction mode. Now boundary between continuous and discontinuous conduction mode, this is called a critical condition. So critical condition is like you can see the current is just touching zero. So minimum value, IL minimum value is 0. So this is the boundary condition, and third one is discontinuous condition. So here you can see that there is an inductor current 0 for a short period of time. So the IL minimum will be less than 0. Value is less than. So this is discontinuous conduction mode. So when we are designing a buck converter, we are always designing for continuous conduction mode. So we have to choose the inductor in such a way that the inductor should maintain continuous conduction mode. Now there are two terms, L critical inductance, and L ripple, that is inductance based on ripple specification. So when you design a buck converter, inductor for a buck converter, you need to always calculate the actual case. When you are actually designing for your hardware, you have to see for the critical value of L and the ripple value of L, like minimum value you have to maintain. So in critical, L critical is nothing but the inductance at which the converter operates at the boundary condition, that is IL is equal to 0. For L less than critical value, if your inductor value is less than this L critical value, your buck converter will show discontinuous conduction mode, and if the L is greater than L critical value, your buck converter will be in the continuous conduction mode. Now another term is L ripple. So there is a peak to peak value. Delta IL is having a limit. Okay, so if your delta IL is smaller, then your ripple will be large. This ripple will be large if your delta IL is a smaller value, and this if the delta IL is a larger value, then L ripple will be a smaller value, lower inductance. So L ripple also should maintain a desired value to maintain the size, cost, and the performance of the performance of your converter. So we have to calculate this L critical value and L ripple value when you are actually designing the converter. So now remember the basic equation of calculating the inductance, and accordingly we will do the calculation. But keep these notations in your mind: L critical and L ripple. Now we will derive the expression for the capacitor value. So this is the circuit diagram of the buck converter. So this is your inductor current. Okay. Now capacitor, this is the waveform of the capacitor current. This is the waveform of the capacitor current, and again this is the TS. One cycle. This is one cycle. Not this point. There is a correction in that. This is wrong. Okay. This is your turn on interval, and this is your turn off interval, and this much is your one cycle. So this is your inductor current. So this waveform is your inductor current, and this waveform is the capacitor current. Okay, capacitor current starts from negative, then positive, then it will again go to negative. This is the capacitor current, and this is the waveform of the output voltage or capacitor voltage. These both are parallel circuit, parallel to each other. So V output will be equal to VC. So this is the voltage across output voltage. Okay, so to maintain this voltage to a constant value, we are connecting this capacitor. So otherwise, if there is no capacitor, your output voltage will also show, output voltage will be also a square wave. You will not get a constant voltage output. Okay, now we will do the derivation, or we will find how we can calculate the value of capacitance. So here IL is equal to, again at this junction we are applying Kirchhoff's current law. So IL is equal to IC plus I naught, or we can write IC is equal to IL minus I naught. Okay, and we know that the voltage equation delta VC, ripple voltage, is equal to charge, change in charge upon V is equal to Q by C, that general equation. So delta VC is equal to delta Q by delta C, sorry, delta Q by C. Now we need to calculate delta Q. Okay, delta Q is nothing but the area of this waveform. So this is a triangle. This is a triangle, and what is the area? This is the base and this is the altitude. Okay, so here the area of this can be written as half into base into height. And what is the base? Base is equal to, or this much is the base. So this total base is D into TS. So this much will be dTs by 2. So here half into dTs by 2, which is the base of this triangle, and height of the triangle. This is the height of this triangle, that is delta IL by 2. So area of this triangle can be written as delta IL dTs upon 8. Okay, so delta Q can be written as delta IL dTs upon 8. So when you substitute this delta Q for this equation, delta Vc is equal to delta Q by C, which is equal to delta IL dTs upon 8C. So from this, Ts can be written as 1 by F. Time period is equal to reciprocal of frequency. So delta Vc is equal to delta IL into D divided by 8C into Fs. So C is equal to delta IL into D divided by 8 Fs into delta Vc. So with this equation, we are able to calculate the value of capacitor. So keep this in mind. So when you listen this video, it is good if you are able to derive this equation by yourself in a notebook along with me, so that it will be easy for you to understand or analyze it later. So these are the two equations what we have derived for capacitor, value of capacitor, and calculating the value of inductor for a buck converter. Thank you so much for listening the video. So I hope it is clear for you how to calculate the value of inductor and capacitor. So whenever engineers design a power converter, they generally follow a systematic approach. So the first step to define the converter specification is input voltage, output current, load current, switching frequency, ripples, and all those things. Based on this specification, we need to find the inductance and capacitance value, and thereby we are able to get that systematic approach to get the reliable converter operations. Okay. So in today's lecture, we understood why the inductors and capacitors are essential in a buck converter. We discussed the role in energy storage, current smoothing, and voltage regulation. Then how incorrect selection of these converter affects the converter performance. So with from next lecture onwards, we will do the mathematical numericals or mathematical calculations for designing the buck converter. So along with the buck converter, we will do the numericals on boost converter and buck boost converter. So in similar way how we have done for the buck converter, you are able to obtain the equations of boost converter and buck boost converter. I will help you to solve the numericals of all these various type of converters. Thank you so much for watching. If you have any questions, please note them down. We will discuss them during our interactive session. We will have an interactive session in between whenever you are available. Thank you so much.